Good morning, everyone, to the third day of virtual INTERGEO. I'd like to welcome you here on the PhaseOne virtual booth. And my name is Carsten Wieser. I'm Integrator Sales Manager for EMEA region. And today we have some interesting agenda for you. And we will show a bit of our integrating partners. Today we have joining in GGS from Germany, who did an interesting Powerline inspection system for a larger power utility company in Germany. And Dr. Gerhard Kemper, who is joining us today, will speak a bit about his integration job, the PhaseOne cameras, and what the project is all about. So he for sure used some of our equipment from our technology, which is the PhaseOne camera series, starting from the IXM camera series for UAV and applications everywhere where size and weight matters, and to the workhorse IXM-RS 150, our most important camera today, with a large coverage on the market already and a very high resolution. Continue with the 4-band system for adding near-infrared channel to all the imagery, and then the two large format type cameras with 190 and 280 megapixel. All are equipped with very high-end lenses with no compromises in optic quality, with a very reliable RS shutter, and with system components like the IX controller up to the full integrated system, the PAS system, GNSS IMU, control of cameras, gyrostabilized mount, flight guidance, and flight planning, all is integrated into a turnkey solution. But today we have the topic with our integrator GGS. We very welcome Dr. Gerhard Kemper from GGS in Germany.
Good morning, Carsten. Thank you for the introduction. I'm happy to join you on your virtual booth on INTERGEO this year. And I would like to present what we did, which setup we used for the Powerline inspection system. I will start a little bit. What is the Powerline monitoring about? So actually what we are looking for are anomalies on the power line, which can be some hotspots, which we discover with infrared camera. We are looking for example, bird nests or other findings directly on the poles. We're looking for the right of way of the power line if there's a vegetation coming too close. This one we are doing with LiDAR. Looking for some other findings like kites, balloons in the power line, typically covered with RGB cameras, looking for the aerial balls, and we are looking also for defects on the insulators, and we are also using here ultraviolet cameras to check out for discharges. So it's a quite complex task to do, and this one is done on helicopters to fly beside the power line up and down, so we can cover both sides. Jumping a bit into the system, so we see here, for example, the power line, and we see here the flight paths. So we are flying offset to the power line, and that's the center, and we of course cover with a laser scanner with first and last pulse the surface structure, the terrain structure. We look for the vegetation which may come too close to the power line, and of course together with the RGB we extract all the photos of all the infrastructure and the surroundings. That's some of the basic survey results what we have. Going for the next slide. Yeah, and what is the setup actually? You see here the helicopter, and we have a laser scanner. In that case, it's a Regal Vux long range to cover also longer distances. We have thermal cameras. Actually, we have 4 cameras installed. We have mapping cameras, and a typical setup which is typically used today is, let's say, with 2 cameras, a thermal and a laser scanner. But the setup what we are using is far more complex. So we have a laser scanner, we have RGB cameras. Actually, we use 5 cameras with forward, backward, and nadir view, and thermal cameras. We are going for extremely high resolution. And we'll go for the next slide. I think one has erased. So we cover typically a GSD solution from 2 millimeters on the power line. That it's really amazing. And we collect something about 200 points per square meter of the power line, and in both directions it's jumping up to 400 points per square meter. And yeah, as you may already have seen, that Siemens is the partner where we're working with on this project, and we want to do, let's say, this inspection more precise, faster, with automatic detection, more integrated, and to be safer because we save flight time, and of course more cost effective. And of course this multi-sensor system gives a huge amount of data. And what the task is on the Siemens side, they are going to use AI for the detection of the mixed combination of all sensors. And of course, it needs a cloud computing. And we want to use it also in the future on a UAV basis. It's a full digitized setup. So we take the RGB camera data, combine it with the LiDAR data, use a corona sensor for the discharges, and also the infrared sensor. Actually, all what we are looking is with these two sensors for anomalies, because the infrared sensor is a little bit difficult for the interpretation because we have a lot of material characteristics what we see in the data. But actually, if we find an anomaly also on the corona sensor, we're looking deeper with the data of the RGB and the LiDAR. And one first step is to have an automatic inventory using already AI to detect where are isolators. So we crop already the images that we, let's say, remove all information which is not important for the inspection itself, because we easily capture terabytes of data in one flight. It's a kind of big data analysis with artificial intelligence, so it's quite big volume on processing, and of course all data are 3D data. And finally, it results in a web-based application where you can zoom in, have all details, all informations, which is then on the customer side, so he himself can look for the findings. They are already marked, and he can decide how to go further, send an inspection team for repair or something like that. So our sensor setup. Okay, it's okay. I see the slide is already marked. So we have, of course, a direct data management system. So with all data coming on IX control and other storage device, we have oblique and nadir cameras. The heart of all the system is a GNSS INS. So everything what we capture with the data is logged let's say connected to the GNSS INS so that we can combine the data easily. So they have exact timestamps. Even the video stream of the corona camera running with 50 Hertz is connected to exact GPS timestamps. So we have a direct referencing device. Okay, it's going the other way around. So that's, let's say, the multi-sensor setup. So we have here the 5 PhaseOne cameras. At the moment, we are using IXU cameras because we started this project 3 years ago. So it was that time the top camera of PhaseOne. Today, we would make use of the IXM 150 for sure. We are using lenses from 90 to 110 millimeters. And with a distance of 40 to 50 meters, we capture data with 2 millimeters, 1, 2, 3 millimeters, depending where we observe the structure. We have the GNSS INS device as a central part here, which is linked to all devices for the laser scanner, for the thermal cameras, which are running, let's say, in a separate loop on a separate controller, and the ultraviolet camera, which is combined with a visual camera. It's looking forward to check out for findings. And of course, we have everything connected with the flight management system, especially adapted for this special kind of missions. Mission planning, of course, we have the geodata but we need, of course, more information. We need the information of the structure that we can decide on which angle we use for the cameras to observe all infrastructure components. This results in a reduced infrastructure mapping, actually, and this results in a footprint calculation, and then finally in the mission plan. And this is a typical view of the moving map. So we see here the images captured, and in flight we have, of course, pilot displays with adapted instruments, speed indicators, because that is very important, because we capture with a high capture rate. So we have to be sure that we are not flying too fast, because we also may have a forward motion blur in that, and we can fly already what is called snake line, so we can fly the curves, so we don't have to fly single lines. So the system is already set up that we can continuously fly a power line and follow all curves and orientations. That is actually the setup. So the cameras are looking sideward, two cameras looking a bit forward and backward. So it's a quite complex pod. So we have the GSD solution. We have an upper camera which looking to the top part of the pole, and the lower camera which looking on the lower traverses with the insulators. And we have a nadir camera looking slightly oblique for orthophoto mapping. That's the 4 thermal cameras. You see here what a thermal image is looking like. So we see here a little bit warmer insulator, but of course you see a lot of metal or material surface informations. So it's not easy to interpret this data, but actually looking for anomalies, it's working fine. And we have also integrated what I already mentioned, this Corona camera. It's a special amplified ultraviolet camera with a daylight filter. That's quite important, otherwise you get a lot of information from the sun. And it's combined with the RGB camera, and it's running with 50 Hertz, because also the power line, the voltage is alternating at 50 Hertz. So we need to be close to the frequency, because a discharge may hold only a few milliseconds. So we want to capture here with a very high capture rate. That is the setup of this camera combined with a second RGB camera. This is an overlay of a discharge on a RGB images. So we can find these things finally overlaid very easily, so we can look deeper if there is something on the wire, if there's something on the insulator, or where is the finding coming from. Of course, we use LiDAR, and we try to capture the catenary of the power line. So this also gives some indication of the of the hanging of the power line, and of course also for the geometric extraction for the survey itself. And in the 2 flights we capture up to 400 points per square meter. So it's the distance, it's the sag of the cable, and we have the height of the poles. And this one is of course important to detect if there are vegetation coming too close to the power line. That is the pod. It's looking like, so it's already grown out of the pod itself. I have a photo a bit closer, and we see here the camera setup hanging underneath the helicopter. Mission outcomes. So that's a standard color image, and with automatic detection we find all the infrastructure on the power line automatically by the AI. So we see here the clamps, the insulators, the chain of insulators, and here some other clamps. Go to the next slide. Hanging. Of course, we extract also the LiDAR data and combine it with the RGB information, and already classify what is insulator, what is the structure of the pole, what is the power line itself. And then, of course, as already mentioned, we have precisely calibrated all sensors. They are combined with GNSS INS, and they finally can be overlaid on the complete data set. And here are some findings. You see here some, that's the image in total. And here we see the findings, and coming closer, you see here that some of these corona rings of the insulators are damaged. And then finally Siemens provides this information to the customer, and they have to decide how urgent they send out a team for a repair. Oops, I was too fast. Here's some other findings. That's the ceramic insulators. The glass insulators are a bit more difficult to identify, but the deep learning algorithms in the AI, they are able to be trained. With every additional flight, they get more information, and they are trained to be better and better, and more than 90% of the findings are already detected automatically. Here we see a hotspot on the some of this insulator clamps. Already here on some repairs on the cable, we find some hotspots, and here it's an example of a discharge of an isolator, so we have this corona effect. Sorry, going back. So that's the web interface. So the customer finally can have it on the map view. He sees the power line and findings on the line or in the surroundings, and he can go deeper and zoom in and has all the informations. And of course, he also has a report on which place, which finding was automatically detected. So this is a very fast and a very detailed and a very precise inspection method. Okay, just going back. That's the new approach. So we are at the moment in a research project, and the camera setup, of course, should be reduced because of the payload. And the intention is to fly also with UAVs. This one is a big UAV produced by Schiebel in Austria that is able to carry a payload up to 50 kilograms. Just fine for the actual sensor setup. And we try to implement, let's say, the complete setup into this drone at the moment. And now I'm trying to start this video.
Siemens.
Okay, that's my presentation. Thanks for the chance to present it here, Carsten, and I hope we have a good day today on the INTERGEO.
Okay, thanks, Gerhard, for sending all the insights to the system. Very complex system with, I think, a lot of integration work you have done. And yeah, but I think it for the power utility companies, it's very helpful tool to come closer to an automated and more automated way to inspect all the infrastructure. So thanks again for your time and joining us in this presentation. And yeah, see you next time.